This video will be a basic review of selected topics from general chemistry. Chapter 1 of the textbook is devoted to the review of general chemistry, so we will begin there. You should be familiar with these topics: atoms, electron configurations, periodic table, Lewis structures, ionic and covalent bonding, and different definitions for acids and bases. If you need to review any of these topics, please do so. We will use these concepts throughout the course, so it is important to have a good understanding and foundation of these concepts. Again, this lesson is only going to be a quick review. What is an atom anyway? An atom consists of a nucleus surrounded by electrons. The nucleus is composed of protons and neutrons. Protons are positively charged, while neutrons are uncharged. Electrons, which surround the nucleus, are negatively charged. If an atom is uncharged, it means that the number of protons is equal to the number of electrons. We can tell how many protons an atom has by looking at its atomic number. The number of protons in an atom never changes. However, the number of neutrons can change to give various isotopes. Electron configurations can tell us about the reactivity of elements. The Aufbau principle says that an electron occupies the lowest energy orbital. The Pauli exclusion principle says that only 2 electrons can occupy an orbital, and those 2 electrons must have opposite spin. Hund's rule states that in same energy orbitals, an electron will occupy an empty orbital before pairing with another electron. This is also referred to as the degenerate orbital rule. Hund's rule can also be described as going up, up, up before going down, down, down when drawing electron configurations. Let's have a look at the electron configuration for lithium and the electron configuration for the lithium ion. The arrows indicate increasing energy. Lithium is in the first group of the periodic table, so it has 1 valence electron in the 2s orbital, which suggests that there are a total of 3 electrons. By following the 3 rules, 2 of the electrons go in the 1s orbital with opposite spin. And then the final electron goes in the 2s orbital. Now, to get the lithium cation, lithium has to lose an electron. If it loses an electron, then which electron does it lose? It loses the electron in the highest energy level. Electronegativity is the tendency of an atom to attract electrons. Electronegativity increases as you go up a column and to the right on the periodic table. You do not have to memorize all of the electronegativity values. The few that you need to know for organic chemistry are simple because they follow a simple pattern. Fluorine has an electronegativity of 4. Oxygen is 3.5, nitrogen is 3, and carbon is 2.5. As you can see, they decrease by 0.5 as you move to the left, so it's simple to remember. It is also helpful to know that hydrogen's electronegativity value is 2.1. Again, electronegativity increases as you go up and to the right. We can use electronegativity to assign polarity. A dipole moment of 0 indicates nonpolar, and a dipole moment other than 0 indicates polar. We can use this table of electronegativity ranges to determine if a molecule is nonpolar covalent, polar covalent, or ionic. A nonpolar covalent bond has an electronegativity value less than 0.5. A polar covalent bond has an electronegativity value between 0.5 and 1.9. If the electronegativity value is greater than 1.9, it is considered to be an ionic bond. Let's practice with this list of bonds. We want to predict if they are polar or nonpolar. For the carbon-carbon bond, we know that the electronegativities are the same, so it will be nonpolar. For the carbon-hydrogen bond, we can calculate that the change in electronegativity is 2.5 minus 2.1, which gives us 0.4, so it is nonpolar. Now let's do the carbon-oxygen bond. Carbon is 2.5 and oxygen is 3.5, so the difference is 1, which falls in the polar covalent range. The carbon-fluorine bond is 4 minus 2.5, which gives us a delta electronegativity value of 1.5, which falls in the polar range. For the oxygen-hydrogen bond, we do 3.5 minus 2.1, which gives 1.4. This also falls in the polar range. For the last example, the nitrogen-hydrogen bond, we get 3 minus 2.1, which gives us 0.9, which is also polar. An incredibly important rule in chemistry is that opposites attract. So, opposite charges attract each other, while like charges repel. Note that charges on atoms need to be circled. Partial charges do not need to be circled, and they are represented by delta. So, if X usually represents a halogen, if a fluoride ion is present, to which atom will it be attracted? It will be attracted to the positive charge, so it will be attracted to atom R. Carbon, nitrogen, and oxygen are three elements that we will use frequently in organic chemistry, so it's very important to have an understanding of them. Carbon has 4 valence electrons, and it likes to form 4 bonds. Nitrogen has 5 valence electrons, and it likes to form 3 bonds. Oxygen has 6 valence electrons, and it likes to form 2 bonds. Lewis structures are important to understand. We will be proposing structures, so this is a necessity. These are some basic rules when drawing Lewis structures. First, we need to add the total number of valence electrons from the given molecular formula. If the formula is negatively charged, you add 1 electron. If the formula is positively charged, you subtract 1 electron. Then we begin by connecting all non-hydrogen atoms, generally making chains of carbons. The next step is to complete the octets around the atoms by connecting hydrogen via a shared pair of electrons, or by giving lone pairs, or by sharing more than 1 pair of electrons. After completing the octets, check to see if the number of electrons in your proposed structure equals the number from number 1. You must have the total number of valence electrons in your structure. Any more or any less is an invalid Lewis structure. Finally, it's important to indicate any non-zero formal charges. Formal charge gives us the charge of a molecule. There are 2 basic formulas we can use to calculate the formal charge. Both will give the same formal charge. So we can either take the group number, subtract from that half the number of shared electrons, subtract from that the number of unshared electrons. Or you can take the number of valence electrons and subtract from that the quantity of the number of lone pair electrons plus the number of bonds. Now it's time to practice drawing some Lewis structures. Let's start with CH4O, methanol. You will learn the nomenclature of many functional groups in upcoming lessons. The first thing I do when drawing a Lewis structure is to make a table that contains the elements in the formula, how many valence electrons each has, and then add them up to get the total number of electrons. Carbon has 4 valence electrons, hydrogen has 1 valence electron, but there are 4 atoms, so we'll multiply that by 4 to get 4 electrons, and oxygen has 6 valence electrons. Adding this up gives us the total of 14 electrons. Okay, let's get started. First, draw the carbon and connect the oxygen to it. Your carbon skeleton should look something like this. Now, we need to fill the octets with hydrogens and lone pairs. After we do this, we need to calculate formal charges. This is what the Lewis structure looks like. Note, show all lone pairs of electrons as dots. Do not show them as tick marks or X's or any other symbols. We know that there are not any formal charges here due to the number of bonds on the carbon and on the oxygen. Let's do C2H6O. Start out with the table so we know how many electrons we have to work with. As normally, we start with all non-carbon atoms, so we have 2 carbons and an oxygen, which looks like this. Then, fill the octets with hydrogens and lone pairs. So this is what we are going for. Now, are these structures the same? Look very carefully. Indeed they are. Some of you may have proposed a different initial carbon skeleton at the beginning, and that is totally fine. There is a constitutional isomer, which looks like this. It is an isomer because the oxygen is in a different location, which means there's a different connectivity. Notice that the top structures are both structures for ethanol, while the bottom is dimethyl ether. Again, we will discuss nomenclature later. The next example is CH2O, which might seem odd at first. Let's work this problem by going with the normal procedure, so first we should generate a quick table. Carbon has 4 valence electrons, hydrogen has 1. We have 2 hydrogens in the formula, so we're going to multiply that by 2 to get 2 electrons, and oxygen has 6 valence electrons. Adding this up gives us a total of 12 electrons. We are dealing with less electrons here. Let's connect the carbon to the oxygen. And now let's fill their octets by connecting the 2 hydrogens to the carbon and adding lone pairs. Obviously, we have formal charges here. Also, whenever we indicate formal charges, we circle them and place them closest to the atom that bears the charge. But let's practice calculating the formal charges. The formula is shown at the bottom of this slide. So the formal charge on the carbon, carbon's group number is 4, minus, it's sharing 6 electrons, half of 6, minus, there are no unshared electrons, so 0. Whenever we perform this operation, we get a positive 1 charge. For the formal charge on the oxygen, it will be 6 for the group number minus half of the number of shared electrons, in this case is only 2, minus the number of unshared electrons, which is 6. This gives us a formal charge of negative 1. As a general rule when drawing Lewis structures, the more electronegative atom typically has lone pairs. The more electropositive atom usually gets the hydrogens. So as in the previous example, the carbon is more electropositive, so it obtained the hydrogens, and the oxygen is more electronegative, so it received the lone pairs. It is important to be able to identify the formal charges. The formal charge will be 0 if carbon has 4 bonds, oxygen has 2 bonds and 2 lone pairs, and nitrogen has 3 bonds and 1 lone pair. Examples of formal charges of +1 and -1 for carbon, oxygen, and nitrogen are shown here. Take a moment to review them. Let's have a look at some considerations for drawing Lewis structures. First, use bond lines to show the sharing of 2 electrons. If an atom has a formal charge other than 0, be sure to show it and to circle the charge. The charge should go closest to the atom that bears the charge. Be sure to show all lone pairs. They should be represented by dots. do not show any lone pairs as X's or tick marks. They are represented by dots. Good Lewis structures typically try to minimize the number of formal charges. The formal charges should add up to the overall charge on the molecule. Circle non-zero formal charges. Overall shapes include linear, planar, bent, pyramidal, or tetrahedral. And as a general note, third row elements might violate the octet rule. Kekulé structures are similar to Lewis structures, but they usually do not show the lone pairs of electrons. As you can see in these structures, no lone pair electrons are shown. Condensed structures essentially leave out the bond lines. Basically, it is just writing what you see in a more condensed form. Take a look at these examples. As you can see, we are literally writing what we see in the Kekulé structure without the covalent bonds. Skeletal structures are helpful for drawing molecules more quickly than writing out all the elements that compose them. They show the carbon-carbon bonds as lines. They are also called bond-line structures. What might seem confusing is that carbons are not shown as the letter C in this type of structure. Instead, each vertex represents a carbon. If there is not a charge on a carbon, then it is understood that they receive the necessary number of hydrogens to fill its octet. We need to practice drawing some skeletal structures. The more you practice, the easier it will be. What I usually do first is count the number of carbons in the molecule. In this first example, there are 1, 2, 3, 4, 5 carbons. This means that we have to have 5 carbons in our skeletal structure as well. When we draw the skeletal structure, it looks like this. And you can see that there are 1, 2, 3, 4, 5 carbons. Notice that the carbon-hydrogen bonds are not shown. Let's look at the second example that has a bromine attached to the carbon chain. There are 1, 2, 3, 4 carbons, so we know we have to have 4 carbons and 1 bromine in our skeletal structure. As you can see, there are 4 carbons here and 1 bromine. Try to complete the last example by yourself. Pause the video and see if you can solve it. The answer will be shown shortly. Here is the skeletal structure for the third example. Do you remember a table similar to this one from general chemistry? There's a lot going on in it, but we really don't need all of this information for organic chemistry. We only need about this much. The main goal is to be able to identify the shape, bond angle, or angles in hybridization of atoms in a molecule. This table can help explain it. Please take a moment to review this table, or to review your notes on determination of the shape, bond angles, and hybridization from general chemistry. Here is the information from the table that will be useful for organic chemistry. Let's have an example problem. We want to predict the hybridization and bond angles of this compound. For the hybridization of carbon-1, there are 3 structural units around the atom, so it is sp2 hybridized. What about the hybridization of carbon-2? It also has 3 structural units around it, so it is also sp2 hybridized. Now on to oxygen-1. Remember that structural units include bonds and lone pairs of electrons. Oxygen 1 here has 4 structural units, so it is sp3 hybridized. What about carbon 3? 4 structural units indicates sp3 hybridization. Now on to bond angles. Let's first look at the hydrogen carbon 1, carbon 2 bond angle. Carbon 1 is the central atom. We said that it is sp2 hybridized with 3 structural units, so the idealized bond angle is 120 degrees. What about the carbon 2, oxygen 1, carbon 3 bond angle? Oxygen 1 is the central atom, and it is sp3 hybridized. This means that the idealized bond angle is 109.5 degrees. Lastly, the hydrogen carbon 3 hydrogen bond angle. Carbon 3 is sp3 hybridized, so the bond angle should be 109.5 degrees. Atomic orbitals are orbitals that surround an atom. We can't determine both the momentum and the location at the same time of an electron in space. This is known as Heisenberg's uncertainty principle. Note that s atomic orbitals are spherical in shape, and p atomic orbitals are shaped like doorknobs or dumbbells. Molecular orbital theory gives us a way to assign electrons in orbitals in space that surrounds a molecule. Essentially, a molecular orbital describes the space around a molecule where an electron is likely to be found. An atomic orbital surrounds an atom. A molecular orbital surrounds a molecule. A sigma bond is formed when two s orbitals overlap at the internuclear axis. A pi bond forms when two p orbitals overlap. Bonding molecular orbitals are lower in energy, which means they are more stable. Less energy means more stable. Bonding molecular orbitals are formed through constructive interference. The sigma bonding molecular orbital is written as the Greek letter sigma. Antibonding molecular orbitals are higher in energy, which means they are less stable. More energy means less stable. Antibonding molecular orbitals are formed through destructive interference. The convention for the sigma antibonding orbital is written as sigma star. When two atomic orbitals overlap, two molecular orbitals are formed, one lower in energy, bonding, and one higher in energy, antibonding, than the atomic orbitals. This figure shows that bonding molecular orbitals have lower energy, while antibonding molecular orbitals have higher energy. Notice that this is for sigma bonds. Take a moment to analyze the energy diagram in the figure. The same is true for pi bonds. This figure also shows that bonding orbitals have lower energy and antibonding orbitals have higher energy. Take a moment to analyze the energy diagram in the figure. One of the models commonly discussed in general chemistry is the VSEPR model. Basically, this model says that bonding and lone pair electrons are positioned such that they are as far apart from each other as possible. This is why Lewis structures give us simple structures of molecules. To wrap up this lesson, we are going to briefly take a look at a few different representations of organic compounds. As we look at these figures, take a look at the bond angles and bond lengths that are indicated. Methane has the molecular formula CH4. The ball and stick model is similar to what your model kit will show. Try to put together methane with your model kit. As we go through the next few examples, have a look at the electrostatic potential maps. These will give you some insight as to which types of carbon-carbon bonds are reactive. Let's look at ethane. Notice the A and E that is underlined in the name. This suffix indicates that this molecule is an alkane, which means that only carbon-carbon single bonds are present. The length of the carbon-carbon single bond is 1.54 angstroms. Now on to ethene. Notice the ENE ending that is underlined in the name. This suffix indicates that this molecule is an alkene, which means that at least one carbon-carbon double bond is present. The length of the carbon-carbon double bond is 1.33 angstroms. Now we will look at ethine. Notice the YNE ending that is underlined in the name. This suffix indicates that this molecule is an alkyne, which means that at least one carbon-carbon triple bond is present. The length of the carbon-carbon triple bond is 1.20 angstroms. To wrap up this lesson, let's have a look at carbon-carbon bond lengths and bond strengths. Generally, shorter bonds are stronger bonds. This means that the carbon-carbon triple bond is stronger than the carbon-carbon single bond. Let's briefly look at the bond lengths and strengths of hydrogen halides. This will be useful when discussing acid and base chemistry, which is Chapter 2 in the textbook. As this table shows, as we go down group 7, the halogens, the bond length increases. This means that as we go down the periodic table, the bonds are easier to break, which will make them stronger acids, as we will discuss in the next chapter.